with the data being the population of SAT scores in the year of 1997, and further indicated that our SAT scores are normally distributed with a given mean 950 and standard deviation 150. Let's now apply our understanding of the normal distribution in this example in a different way instead of finding area. The problem now asks us to find the cutoff SCT score of the bottom 75%. So on our normal distribution bell curve, anywhere on this horizontal axis is an SCT score. So the cutoff SCT score, we have seen that back in the day. We have seen this concept of a cutoff back in those time when we were viewing the video on the standard normal distribution. But a cutoff SCT score here simply is just some score. Any score here that we place can become a cutoff, since the entire area cumulatively shaded inside any bell curve is a 1. So any score we place here, let's say a particular score is called a lowercase value x, it will become, any value there will become a cut, since it's gonna split the bell curve into two separate areas. So as required here, this cutoff SCT score is the cutoff SCT score of the bottom 75%. The reason I put my x to the right hand side of 550, the mean value on the bell curve here, simply because the area shaded to the left hand side here is required to be 75%. And that is for sure bigger than 50% halfway through the bell curve, and that is the reason why I'm putting my cutoff to be somewhere to the right hand side. But how far away from 950? That shouldn't be a problem. So putting it all together, the bottom 75% means the area is shaded to the left from where our cutoff is, and being as large as 75% of the bell curve. And that's the reason why it makes sense to put our cutoff being on the right hand side of the mean value somewhere, since the area shaded to the left is bigger than 50%. And so here I'm going to go ahead and just make it the label. So now in this problem, we are actually given the area here already been given, being a 75% on this bell curve being shaded to the left of that. We just need to find out what value of x is this. That's simply a different way to interpreting the question. And so first thing to start, I am going to find out from where my cutoff is how much area is known. So left area here, and this problem has already given us the area shaded to the left of the cutoff value we're looking for, and so this 75% is our left area, and we simply put that as a decimal. So 0.75 is our left area. And so make clear in this problem that we are not looking for how much an area, how big an area is. We're actually looking for now as a plan. Once the area is given to be that big, 0.75, how far or where should we put our value to have that much data or that much area to the shaded to the left? And so I introduced back in the video lesson where I was introducing the standard normal distribution. Then along the video lesson there, I also introduced the InvZ program. So the InvZ that I wrote served that functionality where it converts an area, supposedly this area being regarded as an area to the left of some z-score. Then we are going to invert that area to come back with a z-score. So after running our InvZ program, my InvZ program, then on that given area, then we should be expecting a z-score, and that z-score here as a plan for now is to be the corresponding z-score of our value x. But keep in mind that InvZ program is simply one program I wrote for my own convenient use, and as well as for my students to use. I want my students to have that, to maintain that capability to work with ZScore effectively. But the main purpose of this program is to find out which ZScore having the area shaded to the left-hand side being 0.75. So InvZ program of mine is not the only tool of doing that. If you never have a copy of my program here, there are tons of software or the web tools that allows you to do the similar functionality. So on my computer here with Microsoft Excel, InvZ is now turn to that InvZ tab at the bottom here, and so with the area specifically given at 0.75, now I am going to adjust that in my left area box here. So 0.75. You can also do the same thing on the TI83 or 84 calculator by calling the InvZ norm program. And to get there, we're going to go second variables, which brings up the menu for all the distribution functions for statistics. And let's now scroll down to option number 3, InvZ norm, enter. So the area, as you have seen, that I enter in the Microsoft Excel file now can be put here. So 0.75, or this is the area already known, given to be to the left-hand side of our Z-score that we are finding. And since we are working specifically on the Z-score on the standard normal distribution bell curve, then let's default these two values at 0 for mu and 1 for sigma. So let's now hit enter. And that is our answer. And let's now turn back to Microsoft Excel to see what the answer looks like with the program that I developed using Microsoft Excel. And so Z-score comes out for that, and usually in 2 decimal places or in 3 decimal places. It's all different in every problem. So how about in this example right in the video here, I am going to take Z-score as the final Z-score for this being 3 decimals. So the Z-score correspondingly with this area, or the Z-score having this much area shaded to the left, is supposed to be 0.674. But so if this was a standard normal distribution problem, then we were done right here. If any of you have already watched my video for working on the standard normal distribution. However, this problem here, we are no longer on the standard normal distribution curve. So one extra step need to be taken here. So remind yourself that Z-score anywhere is famously the value x from our population, any value x in our population. Subtract the mean and divide it by standard deviation. And so algebraically rearrange this equation. So I'm going to create a little bit separate space right here, but algebraically rearrange this equation, we come to an equivalence version, which says the x value can be calculated as mu plus the found Z-score times the standard deviation. So these are 2 different, this is simply just a rearrangement of our famous Z-score formula. However, this formula now has a good usefulness. Once we already had Z-score calculated with our known mean and standard deviation, we can calculate our value for x relatively to this data here. So our cutoff SCT score at this point is ready to be found here. From where mean is being 950, I am going to add the Z-score calculated here was 0.674. I am going to multiply that with standard deviation 150. My final calculation comes out to be 1051.1. And so this is our final calculation value. Now, admittedly, I myself is not a member in the college board committees, or I'm not working at the college board. So my point is I am not familiar with how far to round this problem. So I can only stick with the value that comes straight out from our calculation. But this actually brings up the idea for any viewer who learned from this video lesson, is that when you actually apply your skills into doing a real world problem on your own right here, then be aware about the rounding requirements in every problem here and there. And so now we know that about, or at an SAT score being about 1051.1, then it is then it has an 75% of data to the left, or from where it is, it's the cutoff SCT score of the bottom 75%. Then so, but if there is a 75% of area to the bottom side or to the left side according to the picture here, then there will also be in the same bell curve, but to the right hand side of our cutoff that we have just now found, there will be also an area to shade it to the right hand side. And so this same question, but it could have also been known as this value x right here, aka the cutoff SAT score of the top. But since the whole area of the curve here is 100%, from where the cut here, there is 75% of data to the left, shaded to the left, then the top here must be just the other 25% of data remains. And so another name for this cutoff, this exact same location right here, is being referred to as the cutoff SCT score of the top 25%. And so my point is this same exact problem, but sometimes could be worded as find the cutoff SCT score of the top 25%. The exact, pretty much the same question, but instead of wording it as the bottom 75%, sometimes the exact same problem could be worded as finding the cutoff SAT score of the top 25%. So the only fundamental we keep is that anywhere our value is on this horizontal axis, there will be an area shaded to the left. So our first responsibility is to find out how big the left area to that cutoff is. And so if we were starting this problem from scratch, then the left area, the step where we were finding left area, need to take slightly more steps a little bit. But out of 100, which is always full area inside a bell curve, we're going to subtract the area shaded to the right hand side, in this case given to be 25%. So 100 minus 25%, that gives us how big the area to the left, which is a 75 here. And then that area to the left of our cutoff, now found to be 75, is going to be rewritten as in decimal 0.75. And the rest of the later steps, we're going to find the z-score by running some tool, either using my InvZ program or some web tool to invert an area back to a z-score. And then once we have z-score, we use this calculation to come back to the final value of the cutoff where it should be. The same data with descriptions being given here. Now we have a problem that is asking us to find the 90th percentile, or find the 90th percentile of SAT scores. So the 90th percentile means on this entire axis of all SCT scores here, means right in the middle of the bell curve. We've learned since long ago, since we begin a quarter, that a percentile, any percentile, is a cutoff value. So in this context, we're looking for a cutoff SCT score somewhere on this line that has, so an SCT score needs to be looked for that has 90% of other SCT scores below it. And so, in the way how I just now described the true understanding of the percentile, I need the area shaded to the left-hand side of my cutoff to be 90%. So this is right now, currently we call this the 90th percentile, as according to our definition, a percentile is a cutoff value where it has that percent of other values falling below it. And so that's why here I'm generally describing that as my 90th percentile. But so connecting with what we have just learned earlier in the earlier part of the video, then this is also known as, or aka, the cutoff SCT score of the bottom 90%. And once we understand the true meaning of a percentile in our entire continuous random variable data, then the work to find the actual cutoff or the value of the actual cutoff here will become quite simple. And so having x here being the 90th percentile, what it means is the amount of area to the left, or I call that as a name, left area, right out of the box, 90%. And we don't really need to do any math work. And that is in decimal 0.9. And the next step now is now we know that this is the area to the left of a given value on our bell curve. We need to now figure out, with the area shaded to the left being this big, then what z-score corresponding to our cutoff is that. So to find that, I use my InvZ program, but as I said many times, there are many other programs out there, either as a web tool or as a software program, that allows you to invert an area to the left to find out what z-score that is. And so on the TI83 or 84 calculator, we can again call up the InvZ norm command by accessing second variables, which takes us to the menu that displays all the distribution functions for stats. Let's now scroll down to option 3, enter. So this time I am going to input the given area shaded to the left of our z-score to be 0.9, because this is the area that's known to be to the left of our z-score that we're looking for. And of course, we are still working on the standard normal distribution bell curve, so let's now default these two values at 0 for mu and 1 for sigma. I am going to hit enter a few more times, and now we are ready for hitting enter. So this is the answer that's calculated with the InvZ norm on the TI83 or 84 calculator. In my own InvZ program, 0.9 gives me z-score rounded to 3 decimals, 1.282. And so now the actual value, the actual SCT score being the 90th percentile, or being the cutoff score of the bottom 90%, must be from where the mean value is 950. I am going to add the z-score that we found, 1.282, and multiply with standard deviation of the bell curve 150. Final calculation will come out being 1,142.3. And like I said, I'm just using value that comes straight out from the calculation, but be aware of different rounding requirements in every problem here and there. But as an actual interpretation on this particular example question here, then if SCT scores in that year are being truly as described here in the year of 1997, then whoever in that year earned the SCT score being 1142.3 for the SCT score in that year, then that person would be above 90% of the other test takers in that year. And that's a true interpretation of what this value means in our real world application. From the data with descriptions being given here, now we have this question asking us to find the cutoff SCT scores of the middle 80%. So on our MT bell curve for the general normal distribution, center at 950 and standard deviation 150 here. Now the middle 80% is to indicate that around this center, we don't need to be too worried about how big precisely is 80%, but around that center there will be two cutoff. One of them on the left side we call it X1, and there will be another one on X2, such that or so that shading the area between those two cutoffs will produce 80% of area on the bell curve as required. And so that's what it's called, the middle 80%. I need to have an area being specifically given 80% compared to the whole bell curve, but being located right in the middle, in the center of the bell curve. And that is the reason why, if we're looking back into our question here, then the question is actually looking for the cutoff SCT scores as a plural here. And it makes perfect sense that we do need two different cutoffs so that it can define our area in the middle. And before we can get far, then keep in mind again that, and so now we have worked long enough on this general normal distribution, then we see how heavily connected any of our value with the corresponding z-score. And so from where x1 stands, there will be a corresponding z-score, and let's call that z1. And from where x2 stands right here, my upper cutoff, there will be an upper z-score, and namely I call that z2 right here. And so at this point, to have a nice and clear understanding of this example, how I'm going to solve this problem, I highly recommend that you can go back and view my video on how I solve this kind of middle area problem on the standard normal distribution. But so we have two different cutoffs here, so we can decide to start out with whichever one of them. So in other words, whichever one to start out first, that is completely on your choice of anyone who is doing this. I here choose to start out always, in my own experience, I choose to start out with x1, since the area to the left is a little more direct to find. And also remind yourselves, after we learn about the standard normal distribution, any value on the bell curve has an area shaded to the left. And so this cutoff that we're looking at, x1, that we're about to find out now, has an area shaded to the left hand side. Let's start formulating the problem here. So here I'm specifically indicating our plan here is to find out, to solve for x1 first. So that's the plan right here. So in this picture, from where x1 stands, the red area is shaded to the left, should be, and we're going to call that it's the left area. And so think about this entire area again. I've had this explanation already back in my video lessons on the standard normal distribution, but here I can briefly explain it again. The entire bell curve is 100, but that left area is outside of the middle, and by the way, the black shaded middle here is 80%. So being outside of that 80%, I need to take 80 away from 100. So being outside of that 80%, I'm subtracting 80 from 100. But then subtracting 80 from 100 is simply going to end up with a total area that's include the two sides here. We only want to take this one side. So now I am going to divide that by 2. And of course, these are all in percentages. And so left area here, after this calculation, comes out to be 10%. And of course, we're only working in decimals with these area values. So 10% is a 0.1. And so now, once we have that 0.1, so keep in mind this z-score corresponding to x1 will also have the exact same amount of area shaded to the left-hand side. So in that way, I am now going to execute my InvZ. The point is to invert the area shaded to the left of our designated value of our designated z-score, invert that area here found to be 0.1, inverting it to find out which z-score we're at. And so the z-score I'm about to find here is indeed z-score 1 correspondingly. And so using the InvZ norm command on the TI83 calculator, and with input being 0.1 for the area known to be to the left of z-score 1, this is going to be our answer. And let's see what it says with my Microsoft Excel InvZ program. On my InvZ program, 0.1 as the left area gives me a z-score, and let's say I'm going to use 3 decimal precision, so negative 1.282. And that is my z-score 1 corresponding to x1. And so we have learned from earlier part of this video that so to find x1, all we do now is on this bell curve with given mean 950 and standard deviation 150, all we go now is 950 from where the mean is. I am going to add negative 1.282 is the z-score we found previously, and multiply with the given standard deviation 150. My calculation comes out being 757.7. And a lot of time people refer to this as the lower cutoff, or x1. And so the further we're going into this lesson right here, I am highly recommending that you can view my video lesson on how we find this similar kind of problem, but on a standard normal distribution, because it had all that detailed explanation of mine there. And here allow me to only go brief, because we have more steps involved in this kind of problem. And so being on a bell curve, then these two z-scores supposedly, and we can quickly find that by simply reversing the sign here. So the sign of our z1 found previously being negative 1.282. Now z2, technically we have to reinvent the whole new wheel right here by repeat the whole process. But here I can just simply find out that z2 is simply the opposite sign. So now instead of being negative 1.282, my z2 now is on the opposite side of the mean. And mean is of course 0 z-score. So 1.282 but positive. So that leads to immediately our calculation for x2 is now all set and ready. x2 equals 950. From where the mean is, we're adding 1.282 multiplied with 150. And so final calculation comes out for x2 should be being 1142.3. And many other people refer to this value as the upper cutoff of the middle 80%. And so the same problem, but in case anyone start out by finding x2 first. So for x2 as starts, then if we're starting completely independently, that's starting x2 here, then from where x2 is, notice this center of the bell curve, from where the center of the bell curve coming out here to x2 right here, that area where indicated by my double arrow here inside of that area, it's exactly half of our 80%. So that area there being shaded there is 80%, but cut in half. But that's not the area, but that is part of the area, to be correct. This part of the area here is part of the area to the left side of our cutoff x2 right here. So what's the rest of that? The rest of that is how much that area from the center completely shaded to the left-hand side of the bell curve. So in the way how that picture work, then outside of that 40% or 80/2 right here, then there's another additional 50% of the bell curve on the other end, on the further end. So now 50% added with 80%/2, and we once again we call all that amount of area accumulated there, okay, the left area. And so in this case, calculation comes out to be 90%, or in decimal, the more preferred form, 0.9. Then this area to the left-hand side is shaded to the left-hand side of x2. Then we can easily find out our z2 value. This time is we need to run the InvZ program, run my program InvZ, or any kind of program that invert the area shaded to the left of a value to a z-score. So here the area shaded to the left of my z-score is 0.9, and inverting that area through the InvZ program, I'm gonna come up with my value. Z2 here comes out first with the InvZ norm command on the TI83 calculator. Now I'm gonna go ahead and input 0.9, as this is our known area shaded to the left-hand side of z-score 2. And again, we are going to default these two values at 0 for mu and 1 for sigma. And so this is the z-score for z2 right here. And let's see what the InvZ program from my Microsoft Excel files is saying. So back into my InvZ program. Now if I'm using 0.9 for my z-score, for my left area, I mean, then the z-score here would come out being positive 2.8, and let's use 3 decimals here. So z2 now we found first, and that's 1.282. So x2 now is our next destination. It's going to be found by, from where the mean is 950, we adding 1.282 we found previously. Multiply that z-score with the standard deviation 150, and the answer here once again, and of course we have seen that in the earlier part of this video. So here it's just going to be repeating of that value. So 1142 0.3. And once we found our starting, which is in this case the upper cutoff, then the other value. So now for x1, then the z-score, finding z-score step is as simple as flipping the signs. So here our z2 that we started was a positive 1.282, then z1 in this case take full advantage of the bell curve being symmetric. Then z1 simply just going to be negative 1.282, and that saves us from doing all the calculation. And so now once we have z1 nailed down, then our x1 value will be found by the formula 950 plus the negative z-score we found, negative 1.282, but multiply with 150. And calculation came out for that was 757.7. And once again, this is the lower cutoff, and this is the upper cutoff.